Hello, this is Project 7 with
Gloth, George Hoeferlin.
and Sydney Song, and we're working on modeling the electric field decay of NMDA instigated ephaptic propagation. Besides synaptic transmission, which is either chemical, such as neurotransmitters, or electrical, which is based on gap junctions that everybody knows about, networks of neurons are also capable of ephaptic propagation. Basically, electric field generated by a foreign neuron can activate its neighbors. Slow periodic neuroactivities generated by synchronized neurons can propagate at a speed of about 0.1 meters per second, and these activities can self-regenerate by ephaptic propagation. For our project, we're modifying an existing model to generate an electric field based off of an array of neurons and compare the results to a theoretical dipole to see how well they simulate the experimental data. The existing model is designed to test the following hypothesis. Synchronized spikes generated by a group of neurons can depolarize adjacent neurons without synaptic or gap junction transmission. In other words, neuroactivity can propagate across an array of neurons only by ephaptic effect. We can test this effect by observing the NMDA activated receptor in basal dendrites of the non-stimulated / electric field affected neurons. The existing model does not explain all of the experimental results, and therefore we are modifying it with the aims of comparing it to an electric field decay generated by a dipole to draw a better conclusion about the model.
So the method that we'll be going about for getting this project done is first we received the code from Dr. Duran, which was broken down into 5 separate MATLAB codes or scripts and functions. So our first step was to kind of go through those and get an idea of how those work. Most of it was not annotated, so part of our project was to actually go through, annotate it, and decipher what everything means, and make sure it's commented so that if other groups or other people in the future wanted to use it, that they would know how to do it. So once we got that done, kind of went about modifying it to get what we desired. So the first step after that was to make an array of distances between a center point of the cell slice and our electrode array. So we have a 200 in the X and 18 in the Z array of cells, neurons, somas, and dendrites that we're looking at, and we're pretty much taking that array and condensing it into one central point and looking at how the electric field from the cells as a whole is functioning in that area. So then after that, we used voltages calculated to get the strength of the electric field emanating from that central point and determining what the electric field decay looks like for one of the spikes against the electrode arrays that we will make. Since there's multiple spikes, there's actually 5 spikes that occur in the code, so we're kind of isolating one of those and then using that as a representative to apply to the other ones to get an idea. So we have 3 different directions for these electrode arrays in the X, Y, and Z, just to get an idea of how radially that works in each of those to get a good idea. We're not looking at every single point and making it like hundreds of different points to get the idea. We just want one kind of electric field in each of the Cartesian directions. So once we get that done, we have a typical dipole that's calculated to kind of compare our experimental data from our modification to how a typical dipole acts. So to build upon our setup, we included this image to give a better idea of how it looks. So we have 6 electrodes, a 6-electrode array in each direction, Z, X, and Y, in order to give us a good idea of how the electric decay looks in each of those directions. So for the Z, we are placing the electrode arrays 0.02 centimeters away from the Z direction, so all of them will have the same Z coordinates. However, we'll be altering them in the X and Y coordinates to kind of displace them and get a good overall idea of how it propagates. And then in the Y direction, since it's so small in the Y direction, the soma to dendrite distance is like 133 microns, so we're only going about 0.007 centimeters above the field to get an idea, because by the time it gets there, it'll already decay. And then in the X direction, we're about 0.2 centimeters away, since that's the longest direction of cells. There's 200 cells in that direction, so we want to make sure it's far enough away that we have a good idea. So yeah, we'll set those up and then look at the electric field decay at each of those electrode points. So like I said, our first step was to kind of make the code work and get an idea of how it works. So our first results were getting the dendritic and somatic membrane potentials seen in the top right. We have those potentials plotted against time, and as you can see, there's 5 spikes. So in the bottom picture, we kind of box in one of those spikes. It's from the time points 2300 to 2900 milliseconds. And then also you can see the electric field decay, or electric field over time, occurring for each of those spikes. So now that we had that, we could kind of use the electrode array that we described earlier in conjunction with this to figure out how the electric field decay looks like for one of these spikes.
In this graph, we show the electric field decay in each of the Cartesian directions. We chose to record from a central point in each direction because we determined that it would give us the best idea of the shape of the electric field. What we saw was that the slice acts similar to a dipole because in the X and the Z direction we saw peaks that were significantly larger than in the Y direction. And in order to confirm, we generated a theoretical dipole and modeled the field decay in each of the directions. In these two graphs, we see the decay in the Z and in the X. In the Z direction, we see that the decay from the slice is shifted downwards, indicating that the electric field there actually decays faster than in a regular dipole. And in the X direction, we actually see the opposite effect, where the dipole decays faster than the slice, and we believe that this occurs because as you move from the center of the slice to the electrodes in the X direction, there's a larger quantity of cells, and we think that the cells there keep the electric field at a higher level than the dipole can, and so it is higher for longer. In the Y direction, we actually got some interesting results. As stated before, the peak value was significantly smaller than in the X and Z, which supports the idea that this slice acts similarly to a dipole because it shows a donut-shaped electric field similar to that generated by a dipole on its own. But we had trouble when generating a theoretical value or a theoretical decay in the Y direction, as when we first created the decay, we actually saw a negative peak, and we believe that this is because the slice acts similarly to a dipole that is upside down, where the negative is on top and the negative point is on top and the positive point is on the bottom. And in order to confirm this idea, we actually switched the location of the electrodes in the Y to be below the slice, and that generated a positive peak for the theoretical dipole.
For future directions, a natural extension of our project would be to create a 3D heat map model of the electric field generated by the slice of grain. We have modeled the electric field over X, Y, and Z directions, but it would be good to look at comprehensively the 3D heat map of it. Another one would be modify the code to look at the ephaptic propagation by looking at each individual column of cells. So we take each column of cells and plot their electric field generated, and then we see how that affects the next column cells and the next column cells and so on. And that may give us better understanding of how ephaptic propagation can impact the electric fields of surrounding cells. Another step that we could look at is to take our simulated data and compare it to experimental data obtained from actual measuring the electric field of real brain slices and see how well our model simulates experimental data.